Okay, so it's time to start of the next sessions. And this next session, we have two speakers from Nepal and Italy. And the first speaker is Abhimanyu Pandey from ICT4D Nepal. And okay, so if you can share the slide, please start sharing.
Sure.
Okay, I can see. And could you turn yes, full screen mode.
Is that better? Are we waiting for people?
Okay, we have enough time.
Okay. Yeah, my end is rather short because it's still in research discovery mode.
I don't know. He turned on the full screen mode, but it's stuck something. Maybe. Can you once close the window and reopen?
Okay. Is it showing? How does this look? This is slideshow at my end.
Okay. So,
Does that work?
Not yet. So if it's possible, could you once close stop the screen sharing and turn on the full screen mode and start sharing again?
Share again?
Yeah. Not full screen mode.
Choose slide in my.
Not slideshow mode. Is it possible to change the slide mode and share the screen?
And that's what I did this time. No?
It's not slideshow.
How's this?
Oh, it's yeah. Now it's working. So please, yeah, please start your presentation.
Okay. Might as well present while it's working. All right. Good afternoon and namaste. My name is Abhimanyu. I work for a nonprofit in Nepal. I hope I'm audible. If not, please let me know. So right off the bat, this is still in research and discovery mode right now. We were awarded a project by APT based on integration of LPWAN, basically LoRaWAN, public LoRa, and edge computing, which is based on NerveNet. And truth and disclosure, I've been working with Dr. Owada-san for a long time, and he's helped me a lot. So thank you for that. A little bit about us. We are a nonprofit. We basically are trying to figure out which is the most appropriate solution for any specific location. I think generally there's a tendency to view the world in ones and zeros, urban versus rural. What we don't understand sometimes is even in rural areas, someone's mindset might be different, someone's expectations, their reality might be much more different than just simple labels. So I think we need a much more nuanced approach. That's something which we try to do at ICT 4D. Again, topics which we'll cover are the basics of LPWAN, edge computing, and then going forward, basically, how does this data reach where it should reach and how it can be consumed. So there's some very interesting things going on in the LPWAN world. There's been a recent record of almost 1,300 kilometers of single hop on LoRaWAN. I think most of our things everybody's quite aware. I came across a really nice data rate calculator. I just kept it there just for the sake that people should go there and just look it out for themselves. It's very interesting. There are a lot of data points which one can use for actually figuring out data rates. And to tell you the truth, even I don't know all of them, but it's something very interesting. I think shared infrastructure also, it brings us the question, how much are we going to share? How many gateways, how many sensors? I mean, how much more can we just keep redoing over and over again, especially in the context of Nepal? And I think as we move into the IoT and we talk about models, AI models, I think there needs to be a much more deep level of integration and collaboration. And I think APAN and RENs are really ready for that. Edge computing is basically, so why do we need edge? I mean, basically data is being produced and data is being analyzed. But it's not just the physical distance, it's also the distance in terms of time. So how quickly do you want something to respond? And how much does the rest of the world really need to know? So these are very, again, there's nothing black and white. There's no fixed limit or a number, but something which we need to think about. So just a little bit about how I got involved with edge computing. First met Owada-san during the APT 2020 project. And that's when we just did a simple POC of NICT's NerveNet. We had the base station, base node in 4 locations. And we were able to, send messages back and forth. And so it worked. But that project had so many other verticals that NerveNet part, the mesh part was a little, maybe not that highlighted. So we applied again, and this time it was a pure research project. This is simply figuring out what needs to be done if we are just going to use deploy edge computing for something in terms of early warning system or just a sensor. So the network where we need data to reach the consumer, the service seekers at a specific time. And the real research question which has come up, this was especially relevant after the glacial lake overflow. sometime in August of last year. And much downstream, I don't know the exact number of kilometers, a Bailey Bridge actually got destroyed. And there was sufficient time to let people know. I'm not sure how much information traveled or how fast the information traveled, but luckily there were no deaths, but that was one of the key motivations. So going forward, we are planning to do lab testing in Kathmandu itself, and then river testing within this location, and then maybe do the implementation more in the dry season. So this is a bit of what it used to look like and what it looks like right now. And obviously this entire bridge has to be replaced. As you can see, the access roads have been destroyed. And I also wanted to use this photograph to show that many times an event happens, a disaster event happens. And it's not always 0 or 1. It's not that the bridge is up and running fine and then suddenly it goes absolutely to the ground. I'm sure goats and dogs and some wild animals are still using that bridge to cross, and maybe even some brave people, but certainly traffic is completely stopped. So, and early warning system is not just for before the event, but it's also post-event, especially for the local community. If they need to know something, this bridge is at least 2 hours each way from the next community or next settlement. So that's 2 hours going, 2 hours coming back if they don't have any idea of this bridge. And that's why that it becomes, even post-disaster, it's so important. Yeah. This is a bit of project area. This is Mapya Dudh Koshi. This is in eastern Nepal. We have proposed a couple of sensors and gateways along the river. We also have some environment sensors, which we have yet to decide exactly which. I certainly am keen on forest fire sensors, but I'm not sure how that would work in case of a real forest fire. I mean, what happens to the sensor? Right? So I'm still, that's still part of the research which is going on. This exactly, the sensor, as you can see on the far right-hand side, that's where the bridge is. And the road, you can see the winding orange road is how it goes to the river, and then it comes up on the other side. So where the gateway 2 is, from gateway 2 to the sensor, that's easily 2 hours by a jeep. So that's how challenging things are, and that's why information is so important. If you are in the community where gateway 2 is proposed to be placed, you certainly don't even want to start driving. These are some environment sensors on the forest areas on the top of the hill. Again, I've written environment, but most probably we are looking for some kind of forest fire or heat sensors, and we shall see how that works out. So why did we want to really get into EWS, especially in Nepal? As you can see, almost the entire year, there's something or else is going on. Whether it's flood, after the flood, there are these wet landslides. If it was more of a dry monsoon, then there are dry landslides. And then once it becomes really dry, then you have forest fires. And GLOF, which is glacial lake overflow, that kind of would happen almost any time of the year. That's more global warming, but Nepal certainly is in an extremely vulnerable area. I haven't mentioned earthquake, but because I know earthquake sensors are really, really challenging. And then, so that's the natural disaster part. Then it's human induced. So people sometimes don't have proper electricity connections in their homes. You have a spark, it leads to a house fire leads to a garden fire, which leads to a forest fire. This has happened. Sometimes people don't use their devices properly. For example, I have literally seen people boiling an LPG, which is a liquefied petroleum gas cylinders, to get the extra gas out. And that can cause lots of accidents. Road accidents, and it's almost, if I don't have the data right now, but it's extremely dangerous. Many roads are dangerous for the road design, the speed. So there are a whole bunch of disasters going in Nepal almost the entire year. So basically, and most of the disasters need localized information. A road accident is affects mostly the people who are either on going towards that area or leaving that area. So that becomes extremely important. So how does that information reach the people closest to it? So the traditional LoRaWAN, I mean, I think all of us know sensors and gateways, and at the end of the day, it reaches the data center. It's either you use chirp stack or TTN, and then eventually you process it, and then you again send out information to whoever needs the information. This works well. Sometimes it doesn't work that well. At least we propose that we should use something more of a localized processing, edge processing, and that may eventually send out an SMS, but it should send out local alerts depending on the geology, the topology, and the terrain, and basically who are the main user of that area. This is a small diagram I just to show, I mean, just drive home the point. So as time increases, you have a river flowing, you have at T1, you have a certain flood-like situation. You may get a notice on a gateway. It goes through an edge, and eventually, if you have edge processing within time T6 somewhere downstream, that person can get that alert. If you don't, then obviously once that wave reaches the next sensor and goes through the entire process of checking whether it's actually worth an alert or not. So you can have a difference of at least 4 time units. Time unit is not necessarily seconds, it could be minutes, it could be more. So, but I just wanted to keep that just as a variable. So it shows that you have a certain advantage of using edge computing. So the project architecture, I mean, we are still researching this, and a couple of options, obviously. But mainly it's picking out the stack and also picking out the alert architecture. As I had just discussed recently, previously, floods are very much real time, but what happens once the flood has receded? How safe is it? What are the messages we send? What is the event warning that we send? Similarly, in a forest fire, once the fire has been contained, is it still safe? So I think this is also something which you really need to focus on. In the case of the bridge, I think it's not just the bridge being working or not working. I think we need to have different levels of alerts, different types of a little nuanced approach to exactly what is happening. This is a data flow architecture, which we were discussing with a couple of friends. There are different types of stacks, obviously. Things Network has its own, Chirp has its own. But and I've seen this in the last year or two, there's been so much change in the hardware, which is now coming out. A lot of them are putting edge processing right into the gateway. Sometimes even sensors have some amount of processing within themselves, and so we're still going through this process of just deciding which devices and which data architectures to use. So hopefully in subsequent APANs, I present something which we have decided. The future is really changing. I'm really interested going forward. How does this data, or how is this data being consumed? Which models are we using? Rather than just using it as a simple archive of oh, at this and this time, this happened. I mean, I think, can we do something more with it? There has been so much talk about foundation models, distillations, and AI agents, and something which I think we really need to focus on, whether as we speak of different river systems, even within Nepal itself, rivers have their own way of of living their life, and does that actually require us to have bespoke data structure models for each river? Is each river different? How are they different? So these are just things I think we need to figure out as researchers. I don't have the answers, but we are still at the stage of forming the questions. So that's more or less a couple of more. This is just something which we have been figuring out how to place the sensors, which would be the best way. At least I know the Dudh-Koshi River, which I'm specifically talking about, a lot of rocks, a lot of fast-moving river. Dudh actually means milk in Nepali, and the reason that we say Dudh-Koshi is because it's so white because of all the foam. So maybe placing any sensor in the river bed would be almost useless. Maybe we would need most probably some kind of ultrasonic sensor placed over the river, but we are still on the research phase on that. And so the quick summary of where we are is more the design phase right now, and we are definitely looking and hoping to get input on what happens to all this data, which we will collect in the weeks and months to come, and and how do we build river data models related to early warning system? I guess that would be the better question. And obviously, I'm just the spokesperson, and there's so many people behind any project. Really like to thank the KDDI Foundation and NICT teams. Obviously, municipality, who's a beneficiary, Dr. Sebastian and Mr. Lochin, ICT4D board members, and our team. So that's about it from my side.
Thank you very much for your presentations. So, do you have any questions and comments for these presentations? Okay, I'm a member of this project team, but I have one question. So, if we are now trying to install some sensors or thinking about the feasibility study in some field, that field is, I'm just curious, the mobile network is available in that field or not?
Yes, mobile. Let me just, you know what, this laptop is giving me some issues. Sorry. So mobile is available all over the municipality. That's not an issue. In fact, recently, if you see this orange line, which is actually the main road, which is going right through the municipality, I don't think I can magnify this. I could do this time. So this is the main road, and that actually is going to get a fiber optic cable in the recent future. So, and all the gateways will be placed in communities or near ward offices, which actually have either 4G or fiber optic cable for backhaul connectivity. So the orange line, the faint orange line, is actually the optical. It's the main road, but the optical fiber is going to run through that.
Okay, so someone raising their hand. So please start.
Yes. Hello, everyone. Can you hear me?
Yes.
Yes. So I have a question. Just like similar to the previous one about. I'm just kind of curious when you have these disaster scenarios and when this happens. I mean, how reliable are these mobile networks? Because I guess your system will kind of rely that you will rely on the mobile network for internet connectivity, or am I wrong?
Mobile, yes, for backhaul from gateway to a more traditional, like a stack, yes, definitely. The whole idea is that from the gateway, rather than sending it back to the stack, we actually divert it to an edge, and the edge and edge talk. But that's so how do the edges talk to each other? That again, like this basically T4, time is equal to T4. So yeah, I mean, definitely that requires it can either have its own bespoke point to point. So basically, if this entire area of entire network on this side gets destroyed, at least this can keep talking. But yeah, definitely redundancy. I mean, we can make it very redundant, but at some point, if it's a massive flood, if it's a massive earthquake, even that breaks down. Absolutely, absolutely, yeah.
Yeah. Okay.
But it's just adding a layer of of a stop back. But at some point, even the stop back will not work. Certainly. And then that's why when people talk about LoRaWAN and IoT, I always wonder, would a simple camera with an AI be just a better solution? Just an additional, you put it on a hilltop and just take a couple of photographs. Would that work better? You don't need a person.
And I guess it's like, how do you alert populations? Like, do you use mobile networks or do you have some other means? Like, is it sirens or like?
Yeah, definitely sirens would be there. I mean, SMS is again, it's more like post fact, it's nice to have, but when you're actually out there and grazing your cattle, I mean, very few people might have an SMS. That's why practicality in on the ground level is so much different than what we imagine in the labs. It's absolutely true. Because SMS, you have so much noise going on. I mean, the cattle might be moving. I mean, you might not hear the SMS. You might not feel the SMS. But definitely, if you have something flashing, if you have a loudspeaker, it makes a much bigger difference. Yeah.
Thank you.
Oh, you're welcome. Yes.
Okay. So, any other questions? Okay.
Thank you.
So it's almost the time. So let's move to the next speaker. Thank you very much for your presentation. Okay, so the next speaker is Dr. Simon Glask. Could you share the screen and start presentations?
Yes. Let's see. I'll share my screen. Here's my presentation.
Okay, we can see your presentations. Yes.
Okay, and you can hear me as well.
Yes.
Okay, thank you. Good afternoon, everyone. Thank you for the invitation. Thank you, Yasunori, for facilitating this presentation. So my name is Simon Glask. I'm actually located in northern Sweden. I'm affiliated otherwise with Abdus Salam International Center for Theoretical Physics in Italy. And as well, I'm kind of running my own company working with the delator network solutions. And it's based in Sweden. So it's like I'm a bit having different hats. And today I would like to talk a bit about maybe the alternative approach to the IoT architectures that we are usually seeing. So I would like to talk about some of the benefits that I think we can actually get today from the future interplanetary internet architecture. So let me begin with setting up a bit like the background where this research and development actually is taking place. So this is collaboration that was done between the Sami reindeer herders in northern Sweden Luleå Technical University, as well, located in northern Sweden, at the Baltic Sea, and the Interplanetary Special Interest Group, located, I think, based in US, and yeah, so it's I'm actually having kind of a great opportunity to work with very different kind of people that are actually kind of and I think we are all kind of united. I mean, with the DTN in mind. So it's like hopefully at the end of this presentation, this will make sense. We'll try to kind of elaborate a bit more. So as I mentioned, we're located in Northern Sweden, so that means we're way above the Arctic Circle. And the area that we deploy our technology first, it's actually as you see it here, it's encircled with this red circle, and it's actually part of the two rather large national park. And despite the fact that you could say like Scandinavia like traditionally had kind of good mobile network connectivity, this area still today lacks the any kind of a ICT infrastructure, and that's mainly due to the national park policy. So that means it's like it's not allowed to actually set up any mobile masts or any kind of infrastructure. So there are no roads, there is no power infrastructure in this area. So it's basically just wetlands and mountains. However, as a Sami reindeer, they actually do have like exclusive rights to use this area as a grazing area. So as you see, like these areas that are kind of bordered with the blue lines, these are Sami villages. They're kind of organized in different Sami villages, and they are actually moving their herds from during the winter and summertime, depending on where's the best pasture land for this. So they're moving it from mountains area and all the way down to the coast and the sea. As I mentioned, the entire system is completely off. It can work completely off the grid. And here I didn't mention that we have polar winters, so that means we have a couple of months of basically no solar power that we can rely on, which kind of really defines the how the system is and was kind of built. Reindeers, they've roam freely in Sweden, so it's kind of a so they can actually move. There's no kind of borders. They're not kind of enclosed in any or limited, which means that every year when reindeers are actually collecting or gathering these herds, or they usually gather them twice per year. They basically need to find them. They need to kind of bring them to the same place. And in order to do that, the GPS tracking service is needed. So it's actually easier to find, and it greatly reduces the time and cost needed to gather these herds. And I think this is actually quite interesting, at least from my perspective, like that it's actually, I think traditionally I would say, in order to preserve the traditional nomadic way of the Sami population in northern Sweden, those who are reindeers, I think they are really, really using like the cutting edge technologies, and that goes from satellite connectivity to helicopters, like quads and everything. So it's actually quite a inspiring group of people to work with. So. And before we actually dived into developing our own IoT solution, of course, we actually went through the IoT market and we checked what's available there. And some of these are actually used and were used before and are even used today. And the first one is kind of the most kind of obvious one. It's like we have a GSM-based GPS trackers. And right now we're shutting down the 2 and 3G networks in Sweden. So it's actually kind of big shifts happening now to 4 and 5G. Because people are kind of forced, although it's already deployed, but they're cutting it down. So there's going to be a lot of GPS trackers that now needs to be replaced. The main issue with this is that it's a short battery life, and this actually happens especially in areas with no or poor mobile network coverage. And I think it's usually happens because when the reindeers comes into deeper valley, that it's actually a bit of in a shade of the GSM coverage. These trackers try to reestablish the connection with the mobile network, and by doing that they basically just drain the battery. So the second problem that is kind of relevant for the group of people that I'm kind of work with is that this requires the internet, and quite often areas where reindeers are actually where they need to locate the herds, there is no mobile internet connectivity available. The second option are of course satellite GPS trackers. those are as well used. The main drawback for up until now was actually the price, although that was cut significantly, so they're getting more and more as well popular. However, there is the main challenge remains the battery life. So usually you can get maybe just one update, GPS update per day. If you actually want to get like half year one, or yeah, probably around half year battery life. And in a similar way as a GSM, they required internet connectivity. And then we have as well problem as with the forest, where if reindeers are actually grazing in a forest area, it is an issue sometimes to get a connectivity with the satellites due to the thick layers of snow that's actually on the branches. So it's a very good alternative, but it's still like challenged by many challenges up there. So, and then we have, of course, the LoRaWAN that we discuss a lot today. At that time, when we actually started this project, there was really no suitable GPS trackers. There were many GPS trackers made for cattle, for sheep and cows, but I mean those were having much shorter battery lives and it didn't last that long. I think that actually changed recently. And then I think for us, the main challenge was as well to, yeah, the LoRaWAN is kind of a end-to-end encryption. So it's like you want to have basically internet connectivity. You want to have access to the server in order to actually get this position. And for the raining herders up, there was actually quite important to get on the site, basically positions, if possible, even directly from the GPS collars that were on the reindeers. There was no LoRaWAN infrastructure, similar as so we actually had to build our own. So we did seriously consider LoRaWAN. So it's like we tried to basically, yeah, just build a large LoRaWAN network. And I think we actually hit two kind of challenges. I mean, one was that actually most of these spots that will have this LoRaWAN base stations, they had no mobile internet connectivity. So that means we'd need to somehow chain it from a couple of mountain peaks to the area where we have the internet connectivity. And I think a relative high power consumption made this actually quite hard to implement. So despite the fact that this changes well in the recent years, so it's like I know that we have now it's possible to get the lower-end concentrators that use just a couple of watts of power. I mean, having 5 to 10 watts of power consumption during the Arctic winter, it's actually quite a big challenge, which is one of the main reasons why we didn't took this path. And here's a bit of like shift. So in order to kind of say why we actually choose different kind of alternatives, I need to maybe first talk a bit about the delayed Tor network. So the delayed Tor network was actually designed as a kind of building block of the future interplanetary internet. And what it tries to achieve actually is to bring the similar connectivity as we have on Earth, like in an internet fashion, like in all the way to the deep space. And unfortunately, most of the conventional IP, or TCP/IP protocol does not work. I mean, it does not scale, and it's not possible to deploy to the deep space due to the long propagation delays and many disruptions. So it's like what delay Toring does is actually it applies the store and forward architecture. So if we think about if you want to send the message, like for instance, from the edge of the African continent, you would then you could relay to one of the satellites, and you do this when you actually get opportunity to establish this connection. And in a similar fashion, then you can actually forward this message all the way to the end destination. And in between this, you can have many interruptions. You can actually store this piece of information for as long as it's needed, and then you push it further on the path. It's built around the open standard, and it's called Bundle Protocol. Currently version it's actually 7. And I think one of the main kind of driving forces behind this is that we try to share and utilize space communication infrastructure. So this old communication model where you have one mission and one communication plan is kind of slowly dying out because we have so many devices, so many things actually being deployed. So we need to come up with a better way of handling and sharing resources as well. So it's being adopted by the space agency right now. Some of the industries as well already took advantage of it. So that's one of them. I mean, and it's like, so yeah, the question is like, here's like why we choose to use DTN. So it's like, it's first and foremost, it's kind of a decentralized architecture. So it's like, which makes it perfect for us as it's applicable for the online and offline use case scenarios. As I said, like we wanted that everything kind of works and all the services that we're actually using can be used online or offline. So it means, yeah, even if you don't have mobile internet connectivity, you still want to in some way get the service running. So it's a bit more it's not that coherent. I mean, it's like, or it's a bit more heterogeneous, like network type than a traditional sensor network, where you have basically sensor networks and you just pull all this information to the concentrator and to the server. Here, what we wanted to do is as well to push some data back. So that means that when you have users present in these networks, we want to as well be able to address them, to communicate directly with them. And that's again like one of the motivations for using the DTN. And then we repurpose the D that it's usually stands for delay and disruptions for so-called deep sleep. So the entire infrastructure is actually most of the time in a deep sleep mode. So it's like, and what we've done is actually we synchronize this and give it this can be reconfigured. Right now we're actually using the 4 communication opportunities. So every quarter we actually get a chance to communicate, and you can actually do the multi-hop communication, but otherwise the entire network is actually in a deep sleep mode. So sensors, even sensor here, like they need to as well follow this schedule if they wanted to kind of communicate. So, and it's quite a flexible and efficient protocol. So despite the fact that it's possible to reach quite far, you can actually do the interplanetary addressing and communication. It's still relatively small. So so as I said, like unlike in IP networks where we actually send and we actually do the many we do a lot of handshakes. We send a lot of small packets. What we try to do is to actually bundle all the necessary information into one bigger piece of information and then try to send it over the network. So bundle consists of so-called blocks. And it's actually consists first of the primary block and the payload. Those 2 blocks kind of every bundle needs to be made of. And then we have an option to use the extension blocks and security. So in the primary blocks, we basically have the source, destination, we have timestamps, so there's a couple of other options that you can put. Then we have just a raw payload block that we can encode or not, depending on if you are using the security block. And what's really nice, we can actually basically dynamically add and remove as many extension blocks as we want into these bundles. So, and in order to do that, it's the bundle protocol actually employs the CBOR encoding. So it's actually a really efficient way to encode the data. So instead of having fixed size of fields, these fields are dynamically allocated depending on the size. And after now, it's like when you have this CBOR as well, libraries available for most of the code, most of the programming languages, it's actually becoming a very nice and efficient way to send the data. So the average network overhead is around 16 to 70 bytes. So it's still, so that means that it's still possible to do it over LoRa. You could say it's a bit heavy, maybe so for some application, but I think it's actually well worth to do it. So and how we actually implemented this. So first we have sensors, and we use 2 different kind of sensors. I mean, it's like the first one is the reindeer GPS tracking collar, where that are being carried around by the reindeer herds. As I said, like we kind of replace them basically after 2 to 5 years. I mean, depending on the life of the reindeer as well. The entire system is 3D printed, so we started as due to the limited time, we actually had to kind of use the 3D printing just as do the prototyping, and we actually figure out that it works surprisingly well. So we're just basically 3D printing even enough now for production all the sensors and most of the and any other equipment that we're actually using. So it transmits the position only when it's in the range of the base station. So it actually tries to listen if it gets some beacon from the base stations. Otherwise, it tries to store the information. It can be adapted how often they're doing the GPS acquisition. I mean, how often it acquires the GPS and how often it sends out it from 15 minutes to 1 day. And it weighs around 220 grams. So some of the key challenge was the power management, how to make it power efficient. And then antennas as well, as we're actually using the 433 megahertz band, I mean, which means the antennas are rather large. And we started with having basically the dipole antennas on this, just kind of a piece of wires, and this turned out to be quite a problematic. So actually, what it turned out that we, despite of any material that we tried to use, is like due to the Arctic in winter time when you get basically ice building on these antennas, and the material gets quite fragile. Any moving pieces were just basically falling off. So it's like right now we have a just built-in antenna, which was kind of a challenge to build it in a small compacted format due to the fact that antenna, I mean, we have quite a large batteries inside, so that it's a big piece of metal that really affects the antenna performance. So, and for the waterproofing, we actually as well we just started to use the gel and pot the entire electronic together with the battery, because there was really no other solution, despite the fact that we tried many kind of different methods to seal it due to the high temperature changes between the winter and summer. You get air and you get condensations regardless of how well you seal the package. So the second kind of sensors that are not actually, we just kind of tried them. It's like, but it's that I think maybe worth mentioning. We have the ice thickness buoys. So it's these buoys that are actually anchored under the ice on these lakes, and it actually uses the ultrasound and pressure sensors to determine the ice thickness, and then actually this is sent out over the LoRa radios, and it's kind of picked up by the base stations that usually needs to be kind of located close to the somewhere or along the shore. We did had to adjust a bit the antennas to kind of work well under, but we actually got quite a reliable connectivity up to maybe 1.5 meter under the water surface. Of course, this we talk about only the lake water, not salty water. Base stations here in the background, you see how we implemented the base stations. As I said, we cannot really build any infrastructure up in the mountain. So most of these base stations are actually mobile. So this is how we see that we've done the deployment. So you basically connect them one to another, and then you drag them up to the mountain peaks during the winter times. And the most expensive part of this is it's the antenna itself. We are using the high gain antennas, and yeah, they're cost around $1,000. And this was the only type of antennas that actually survived the winter times, because of so much ice and snow buildup on these antennas. Any other types were actually breaking quite fast. So there as well, solar powered. So we see we have solar panels attached to it, and a really large LiFePO battery. Here, what's interesting, we try different kind of approaches. We try from having kind of a higher voltages and 12-volt batteries, but any kind of a voltage conversion takes a bit of efficiency away. So right now we're literally feeding battery power straight into the board and to the CPU. So we're actually working on between 3 to 3.6 volts, depending on how much the battery is charged. It is possible to connect with other base stations, and on this edge of our network where we have a mobile network coverage, they are using the GSM network to offload the data to the server. We use the MQTT protocol to do that, but now we're actually moving to the bundle protocol even for this. So I think what's interesting here as well to maybe mention is that as we use only 3.2 volt batteries to kind of feed these base stations, it became really important to use very thick cables. So despite the relatively small current peaks, we actually had quite some issue due to it. So it's like if anyone else does this, is like this, it's like consider that as the voltages are so small, cables and voltage drops can occur quite quickly. So and I think this is actually one of the particular, and this is different thing that we've done in comparison to the LoRa WAN. It's actually we designed so-called pocket nodes, and in the background you see a couple of iteration of this, and it's actually a device that bridges the LoRa DTN network that we have with the Bluetooth on the other side, that can actually connect to our Nomatrack application. And by doing that, you actually can really literally tap into the network, and you can actually get direct access without any mobile internet connectivity. So you can actually get the data from the GPS collars or from other base stations or other pocket nodes in this network. It's based on an RF52 chips. It has built-in GPS. And as you see here on the right, we actually ditched our own design as we found out that, you know, really go like, I mean, we can actually get off the shelf really nice devices for much cheaper price. And so we actually adopt the firmware to run on these devices. And the last is like, I mean, it's kind of implemented our mobile app. It's built on a Qt, and it actually, as I said, like work completely in offline mode. So that means all the maps and everything kind of are built in. We're using the standard MQTT and SQL stack on our server that we use primarily as a backup, and as well, like if people are actually not on the field, they can actually connect directly and get the data online. And the main functionality is basically it shows the position of the herd, and in addition to that, it is possible to send short messages that can be as well geotagged. So they can appear on the map, or you can just send it from one to another. It is possible to send out as well SMS messages using the SMS gateway. So it's actually, if you put the phone number instead of the channel number, you can actually send it out as well that way. Some of the main challenges, it's like we have different kind of approaches at the beginning, like how to do the timing. Like, so it's like, so we wanted to do time division access first, as we have GPS and we could really sync it well to avoid any collisions. But actually we figured out quite soon that, due to it becomes quite hard to actually get this time division right, especially when you have such high temperature fluctuations and different kind of software implementation. So at the end, we just opted for the slotted Aloha approach, and which is kind of easier to implement, and it turned out to be much robust in our situation. We can actually dynamically define, for each of these base stations, how many slots, and all this timing can be adjusted remotely as well and adopted as well dynamically. Surely one of the biggest challenges was how to assure the backward compatibility of the system. So, the GPS collars that were already up was hard to then change, to make some bigger changes in the protocols, and even changes we've done. We had to kind of hack it in order to make it work. So this became actually quite a challenge at the end. What's interesting as well, it's like the different Samuel villages was as well, they choose different ways of how they place their base stations. So some villages actually, and some rain herds actually opted for the high mountain peaks that gives it a really good coverage. And some other, they actually decided to go with the lower peaks, and it was kind of a bit confusing to me, like at the beginning, but after seeing how they work, it is interesting to see that, those who actually opted for the high mountain peaks, it's much harder to access these sites. So maintenance becomes really expensive, as you need to use the helicopters to actually go. It's like fly there, you go there, it's like and do the maintenance. In addition, like these high mountain peaks, they are much more exposed, so that means you have a much more harsher weather conditions. So it's like much more often these sites actually are affected by some ice damage. So it's like, as you can see on the right side, it's like, so basically if you come here on this site and during the winter time, this entire thing is just like a big clump of ice. So it's like probably like 2 meter high and like maybe 1 meter wide. So and when this ice starts to melt, it can really drag down all the cables and antennas as well. So, and the other some villages actually choose the low mountain peaks. So they actually have they needed more base stations, but they can actually access them with a snowmobile. So that means the maintenance became much easier for them. So I think it's just interesting how the governance and maintenance actually was implemented differently. As I mentioned previously, it's very expensive to do the on-site maintenance. And I think here what's crucial that we actually had to train the rainmakers themselves to do the basic maintenance of the system. There's really hard to find any economical model that would actually basically run this system. So only rainmakers themselves can actually run this, as they're already present on the site, and it's as long as they know how to do it, they can actually maintain. And I mean, we're still kind of start looking after some good business and economic model to run these systems. Like, so, right, so far we actually use it, using different kind of innovation funds and non-profit kind of a funding. And it is something that we're actually looking at the very moment. I mean, how to actually run this in a sustainable way. Most likely this will never be very profitable as it's the quite rather small community. So, and in order to do this, we're actually building the second generation of this so-called DTN of things stack. So we are actually right now developing an open source software and hardware. So it's going to be possible to get the not just software, but as well hardware that will kind of run the DTN protocol. And for this, we're actually making a tiny DTN implementation of bundle protocol for sensors. There will be a bit larger DTN and Arduino library as well that will be implemented on these base stations. We will continue to use these pocket nodes. We're actually planning to kind of use this other one that it's actually quite popular among the mesh static community. So actually try to get the bundle protocol running on this and actually integrate it into the rest of the system. And then we'll use the IONE. So it's like it's an ASUS implementation of the bundle protocol to run it as a backend. As I mentioned, like we'll move purely now to the bundle protocol v7. Previously, we had some proprietary protocols used because we want to kind of save on power. But as it turned out, like the transmissions in our system, they are kind of they contribute to a smaller part of the power consumption compared to the, for instance, GPS modules. We do have an issue that most of this base, I mean, it's like this entire network now just merged into one large network. We thought the base stations will not talk so much with each other as they do now. So we will need to go from epidemic forwarding, and we'll most likely use the probabilistic routing to actually limit where and how the data travels, especially over the base stations. And this is, of course, to address the kind of duty cycle that we're allowed to have on this ISM bands. So we're expanding the current network that's been deployed in Sweden, and hopefully we will get some deployment done as well in Nepal. So it's like we're actually searching for and looking into potential collaboration there as well. And lastly, I mean, this entire system will be integrated into the IPN-SIG global DTN network. So, and maybe a few words about the IPN-SIG. So it's a kind of now we became an Internet Society chapter now. It's called Interplanetary Chapter. And the group that I'm leading, it's called the Pilot Project Working Group. And the main idea with this is to kind of develop and test and refine DTN protocols for the interplanetary internet. It can be actually then used on Earth or space applications. So it's kind of members are having really diverse backgrounds. They're coming from academia, industry, space agency individuals. We're having kind of meeting every second Friday. And what we're trying to build here is, like, as you can see here on the background, we're actually right now building kind of a interplanetary backbone. So we're actually try to have a nodes running, globally spread nodes running on this. And we're actually now planning to include this LoRa based DTN networks into this as well. So we actually now try to expand this current network that we have right now into the sensor network as well. So here I attached the QR code to the link if you want to join the group, if you have some ideas how to, if you have some proposal for some project, or you would like to just join the group and see what we're doing. So I would like to finish with this photo. So this is how the spring looks for us. It's like, so this is how these base stations that are located a bit more exposed areas, they get encumbered in a very thick, more ice than snow that we're usually then knocking off during the springtime when we're checking, maintaining, and updating software. So I think my time is out. So thank you so much for your attention.
Thank you very much, Pastor Samu. Do you have any questions and comments? Yeah, I have many questions. This so you're very working very challenging field for the especially for the physical battery problem and the networking problems. And you are using the DTN bundle protocol, existing open bundle protocol, but that bundle protocol is over the IP networks. So if you want to shorten the packet size, maybe it's a little bit, you need to customize some existing IP protocol stacks. So how do you thinking such thinking? For example, the IP 6LoWPAN protocols are compressing the IP headers. And do you combining such technique to adapt the bundle protocols? Or?
Yes, so basically what we wanted to do is like, I mean, and this is kind of one of the goals of this group is to basically run bundle protocol over a different and very, I mean, it's like a different kind of a, it's called the, I mean, the IP is only one of the technologies we can run bundle protocol over. So we are actually running LoRa straight on, I mean, it's like we're actually running using the LoRa as well and run bundle protocol over the LoRa. So basically you can use it basically on any kind of a communication infrastructure that is there. So the only limitation with LoRa is actually that, yeah, the bundles needs to be quite small. But we are actually as well just now, right now, it's like working on that problem. So it's like we will actually use the bundle fragmentation. So that means you will actually chop the bundle when you're sending over the LoRa network, so that we'll be allowed to kind of send a larger, bundles over the LoRa network. So, but right now we're actually the experience that we're running, so we're actually running DTN over the IPv4, we're running DTN over the IPv6, we're running DTN over the LoRa, so that's actually something that we actually have even part of the network. We're actually running LoRa here locally. So it is possible to, if you connect one of these DTN nodes, it is, I mean, in one of these base stations up there in the mountain city, you can actually send and receive bundles over that as well, with the limitation of 200. Yeah, I think we get around 170 bytes of payload. So it's rather small, but if we fragmented this, then we can actually get much larger bundles through this. So it's like, and yeah, it's like, so the idea is to actually have quite a diverse set of these convergence layers under, and that we actually run them. So run them over a different kind of a technology. So it's like what I'm trying to really push in the group that we're working is that we're not actually just, you know, using the IP technologies. And we want to kind of move away from the IP technologies and the problems, especially with the, I mean, TCP IPv4 that are behind this. So so if anyone is interested, like, I mean, it's like, please, I mean, join the group. It's kind of free. It's like, we do quite some interesting things. So,
yeah, thank you very much. And do you have any other questions? And I also one question. So the internet, interplanetary internet, that is, I'm not familiar with that field. So could you explain what is the interplanetary internet itself?
So yeah, so it's like, well, the idea with the interplanetary internet is that yeah, it's like, so basically the TCP IP stack does not work well especially when you go, you know, I mean, in a LEOs, I mean, like low Earth satellite, I mean, it's like, or up to the moon, you can still use the TCP IP, but as soon as you will go to Mars or a bit further, when you have like half an hour propagation delays, I mean, the TCP IP stack will fail. So there actually is some attempts to kind of tweak, and I think there's right now some discussions to use the QUIC and IP to kind of go into the deep space, but that's actually more of a hack, and it needs to kind of, you need to establish the connection before you launch something and things like that. So it's like DTN was designed primarily to basically have an infrastructure that we can all share and use for the interplanetary internet. Saying that, I mean, it's like, I think right now we have a lot of commercial actors that are, not adopting the bundle protocol, and they have their own proprietary protocols. But that does not mean that, in a just maybe a couple of years, it's like if you will have, for instance, like some rovers, some like services, let's say, on Mars, you will be able still to use DTN, despite the fact that, they will have some other underlying technology to kind of communicate. You will be still be able to to use bundle protocol as well. So I see it as a bundle protocol as one of these ways as well to standardize space communication. So that means, if you'll develop your service that will adopt the bundle protocol, you can basically run it over any kind of a space links that is available. Or yeah, it's like more conventional TCP/IP technology. So it's kind of a, I think it really offers a lot. So it's like, I mean, it's been actually, it's slowly, I think, getting traction now. I think so. I mean, the current the plans now is to actually have like, so DTN stack is actually planned now for the Artemis mission, like on the moon. So the lunar network that's kind of built is having the DTN on a site. It's not kind of it's maybe planned right now for operational use at the very moment, but it is actually being adopted and deployed. So it's kind of slowly gaining traction. And I think just the number of implementation as well are running, so it's kind of easier to use it today than maybe just 10 years ago. So because the first project that I work actually was, we done the work with the Renninghurst, and we actually used these remote villages, and we flew in the data in and out from these villages. That was way before the any kind of a cheap, affordable satellite connectivity. We flew in and out the data using helicopters as data mules. So we actually had a kind of base station in this village, and then you had the 2 helicopters scheduled in and out, so you could actually transfer the data there. So, and we run email, podcast services, web services over this kind of a link. So I think it's actually really brings and kind of a it's a very universal protocol. So and relatively lightweight compared to other stacks. So
thank you. So Abhimanyu-san raising the hand. So please.
Yeah. So obviously, Sam and I we spoke a lot about this, and it's always wonderful to hear. So it's like it's important, but not urgent or emergency kind of messages really work well, right? Because once you start bundling things up and chopping and snipping and snapping, I'm just wondering, something like this, maybe we can also experiment in the project in Mapia as well, because the problem with many of rivers in upper regions of Nepal, because they are in the shadow of the GSM network. So sometimes it just doesn't pick up, and unless you really have a fiber optic cable running. So I'm just wondering, I think we should just maybe talk about this, since we are such at early stage of this, design. And we have been speaking about this for a year, so many months. I mean, thanks to Prashant, who's actually in the conference right now.
Yeah, exactly. So it's like, I think it would be a great idea, especially like, I mean, I hope that we'll get some first prototypes now of this open platform that I'm kind of pushing is to kind of available probably before kind of a summer. So I think it would be really good to actually try it. So, and I think this thing with the that's why kind of my question was as well, how reliable are these networks? Because I mean, it's like from my experience, like when you look at these disaster scenarios, like, I mean, first thing that kind of goes down is actually the connectivity. And even if the base stations are there, just because they get overloaded, like, and yeah, you actually you cannot always rely on the mobile connectivity in these scenarios. And this is something that happened like even in the field that we work, like for instance, we have basically one of these villages actually that still is kind of on the edge of the mobile network connectivity. Is kind of connected by the chain of the mobile stations that are kind of changed deep into the mountain region. And when that one base station goes down, there's kind of an entire village, quite a big community actually, that it's completely cut it off from any kind of a services. And I think what's interesting, during that time, people were actually still able to track their hertz and even communicate with each other. So I mean, it doesn't happen often, but when it happens, it's actually this kind of a solution that kind of we provide for them. It's actually really, really useful. So it's kind of sometimes as well vital for their work. So it's yeah. So I think we have kind of similar situation that you're kind of
it's like a backstop to a backstop. It would be interesting. I mean, since we are researchers, we are doing research, we're trying to figure things out. I mean, so it might be worth, I think. Let's have an offline.
So, and I mean, saying this is like, I don't want to say that, I don't think DTN is kind of some magical, because sometimes, it's not a magical protocol. And I actually have to say, being so universal as it is, it's like it does not solve some particular problem. So that's why we are actually having different kind of a projects where we actually try to address. So it's like DTN network that we'll be using up in the northern. I mean, it's like Sweden will be probably completely different than the one maybe in deep space. But I think still it's quite fascinating if you think that it's a bit absurd, but because like like some astronaut on Mars will be able to ping, a reindeer in the northern swim using the same stack of protocols. I think this is where the real power is from the DTM protocol that I see. So,
Thank you.
Yeah.
Okay. So, is there any questions?
Hi, Samo. So I just wanted to thank you for giving us this kind of presentation here in this community. So maybe hopefully the APAN community could collaborate with this kind of the DTN project in near future. Thank you.
Thank you, Prashant, and thank you for inviting me. So it's like, I totally agree. I mean, it's like, unfortunately, it was too early for me to attend the first part of the session, but I'm quite impressed with the session that you actually have on IoT. So thank you again for inviting me.
Okay, so it's a time for this session. So thank you very much for two speakers, and also thank you for attending this working groups. So it's a very good opportunity to discuss and share this kind of information. And please join the next APAN IoT working groups, and hopefully please share your activities in these working groups. Okay, let's close this IoT working group. Thank you very much for attending.